All right. Okay, so hello everyone. Welcome to episode 50 of Warsaw Quantum Computing Group meetups. My name is Pavel, and it's my pleasure to moderate this meetup for you. Today we have a great speaker, Joan Falco Roget from SANO, and he will give a talk on the use of quantum technologies to discover brain structure and function. So as you can see, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. And I've also agreed with Jean that if you have any questions, you can also interrupt, so we can try to make this this webinar more interactive. But I suggest you to first post your questions on our chat, and when there is a break, I will try to just read your question. And of course, at the end, there will be a Q&A session as usually. Before we start, I would like to thank our strategic partners, Kogit, Narto, and Sonovero R&D for supporting us, and our honorary partners as well. All right, so Sano is one of our honorary partners, by the way. So we have a speaker representing one of our partners, which is great. So I think we can start. So I will now stop sharing my slides. And Joan, if you are ready, you can start sharing your slides.
I will find my screen, which
Okay.
hopefully, yeah.
Yes.
And okay, and everything's fine, right?
Yes, I can
Awesome.
see your slides, and looks good.
Perfect. So I will start timing. Okay, perfect. So yes, I'm Joan. Thank you, Pavel, for the introduction and the invitation and the possibility to present our quite recent work, which was jointly done with Marcin Wierzbinski, who is a former student of our lab, and I believe now is at the University of Warsaw, and Alessandro Crimi, who is the team leader, the PI in and basically what we did is the idea was to try and present the use case of quantum technologies or quantum devices or quantum type of a technology that uses let's say quantum technology in order to let's say solve a numerical problem in that is very common actually in neuroscience, which we phrased it as to discover brain structure and function, which basically means to try to partition the brain understood as a network in different communities that have either a structural meaning or a functional meaning. Since I will start by giving an overview of what we understand by network neuroscience and how it's the whole pipeline from the patient, since the patient arrives at the hospital and undergoes one very specific type of scanner, and how can a simple person like appear or go to the hospital and end up in a quantum computer. Because I'm not sure how familiar is everyone here with this type of workflows. So we are focused mainly in MRI scanners, so magnetic resonance imaging, which is, I can have a pointer laser, yeah. Which is a very big machine that you put that you have in a hospital, and then you undergo what are called different modalities. So the most common one is just a static 3D image, which is called T1 weighted or T2 weighted, that more or less takes a picture of the anatomy. Then you can take functional MRI, which is a temporal scan of the brain and sort of measures the activity of the brain. You can measure it while a person is doing some specific task, or you can simply measure when someone's sleeping or just resting. And you can also measure what is called the fibers of the brain, which diffusion magnetic resonance imaging, which also has some sort of temporal structure, the data, but the meaning is not on the time domain, but it's rather on the diffusion of the water inside of the brain. And you can get some decently, now I would say, some decently accurate mapping of how the fibers in the brain are. The next step is to reconstruct, to have some sort of virtual brain, virtual image of the brain, a virtual mesh, let's call it, depending on whether you are interested only on the surface or also on the insides. And what you do is you basically divide this brain into different regions, macro regions, so at the macro scale level. And there are many reasons to divide the brain this way. There are many also criteria to divide, but the important thing to us is that the brain can be parcellated. So the word here is parcellated into a different number of regions and so it can range, in some cases, the simplest one, I believe, go from 40 to the more complex ones, which go over 1,000. So the idea when you use diffusion MRI is that given the diffusion of the water, you can have some sort of, this should rotate, you can have what is called a spaghetti file, or more precisely a tractogram, which basically is a map of the fibers of the brain. And the way you reconstruct a graph or a network from this image, from this object, is that you basically count how many of these files, they are called tract or streamlines, start in, for example, region in this region, in this pink region, and go this way and end up in region that is red. And you basically count how many go from here to here, and you put a number in what is called an adjacency matrix that simply codes how many connections go from here, from region number 1 to region number 2, etc., etc., etc. So this is the whole workflow to obtain what is called the structural network of the brain. And as I said, as I mentioned before, you can do similar, of course it's not the same, but a similar idea with activity of the brain. So what you do is that you have this temporal sequence, you average across this region in here, and you obtain a series. You do this for all the parts or all the regions of interest, all the ROIs of the brain, of the parcellation. In this case, you compute whatever similarity matrix, similarity measure you prefer. Usually it's the correlation coefficient, and you basically input the similarity between region, the pink region and the red region, and you input a number between -1 and 1. So there are some differences here. This is a strictly positive matrix, and this is it has negative and positive values. And as you can see, this is very different, right? So the structural map of the brain has clearly you can see clearly two hemispheres, the left hemisphere and the right hemisphere, and some connections in between the hemisphere. But in this case, there are also some so the similarity exists not only in what is called in between regions of the same hemisphere, but also strong similarities occur between hemispheres, right? So there are some differences. There's a very interesting line of research that aims to understand how this explains this, or some people even saying that how this explains this, which is very interesting as well. So this is the overall workflow. Since you have someone undergoing a scan in the hospital, and you end up with a mathematical object that is treatable. The interesting idea also, and is basically what we are focused or mainly interested in our lab, is that we study disease. So basically brain lesions, mainly stroke and brain tumor, but also other ones. In the case of precisely a brain tumor or a stroke, which you can apply the same exact workflow, but in this case, you don't have a healthy brain, so you don't have a healthy network. So this is a very common workflow, and we are focused to understand these kind of networks in these kind of scenarios. A very, very, very simple example, if we imagine a brain, so instead of 90 regions in this case, we imagine that it had 3 regions. You have you can have, in this case, 3 different connections, or if you account from 1 to 2 and 2 to 1, and from 2 to 1, you have 6 different connections. And the adjacency matrix, so this is a word that's going to pop up quite a lot. The adjacency matrix is simply codifying that there is a connection from 1 to 2 and that there is a connection from 2 to 3, and vice versa. Importantly, these matrices are symmetric. There is a third type of brain connectivity, which I will not talk about, that deals with asymmetric matrices, but so it is not straightforward, the generalization of any graph theoretic measure to asymmetric matrices. So hopefully now an overview of how can we obtain neuroscience data coming also from non-healthy people, and how we end up with this kind of data. And now perhaps a bit more quantitative is how can we measure the brain once we have this network. So the idea is clear, because since you have a network, you have a graph. Graph theory is a very well established topic in math, so you can apply very well known or really invent new measures, such as it has been done in the last 20 years. The most famous one, if anyone is interested in this kind of graph theoretic measures to study brain connectivity, is this paper from 2010. It has over 10,000 citations, some maybe even considered the Bible of what this is called connectomics, so the science of connections in the brain. And it's very, so if anyone is interested, I recommend going there in detail. But of course, 23 years have passed since this paper, and some people have pointed out interesting flaws, non-trivial, but very interesting. And I particularly like this paper from Chung and colleagues. It's a very long paper, but it's very illustrative, where you have clearly 4 types of networks, which are not only different, but very different in this case. But they have some network measures that are not only similar, but in this case, identical. So this is a clear flaw, that we are trying to study the brain using some methods that are that do not, in a way, disentangle exactly what is underneath the statistics, right? Because this is called statistical connectomics, and there are some correlations between measures. So global clustering, global efficiency, local efficiency, these are different measures from these techniques, and they are correlated in some cases more than others with another type of measure, modularity, which is in our case the one we are interested in and the one that I will talk about. Other methods to understand other problems that come with this approach is that, of course, MRI scanners are noisy, and you have to treat these images appropriately. You have to denoise, you have to do the appropriate treatment. And in some cases, you also have to put artificial thresholds as to detect, okay, this is noise, this is not noise. And you can also binarize. So if a connection is higher than a specific number, you obtain a binary network, which is the example that I showed, the previous very simplified example. And the selection of this threshold is very problematic. Some people have tried to understand or to establish some basis about thresholding, but it's still very, very arbitrary how to do thresholding. And the results clearly, so the threshold clearly has an impact on the result of the statistical connectomics, on the measure that you're using. This is also a fun example that we noticed. This is from ourselves. When you have a network and you like vary the threshold, your entropy of the network decreases, and another quantity, increases. So the selection of this threshold is clearly a pitfall. Interestingly, some other people, another line of research which we are also interested, aims to solve the necessity of having a threshold, but in opposition, it increases in complexity a lot, not only in the interpretation of the results, but also in the immediateness of how you want to apply these techniques. And it's basically looking at the topology of the network. So topology is a word that uses holes. is a field that that tries to characterize networks based on the holes. But this obviously increases both in computational complexity and in the interpretability is a lot harder. I'm mentioning this because there is a possibility of extension of using quantum resources to this problem as well that I will briefly mention in the end of this talk. And another possibility, which is very interesting but not easy at all, is to go to the cognitive domain where you basically design some artificial neural network with more or less similarity to real biological networks that are found, depending on the level of abstraction that you want to achieve. And you train this network to do a task which is emulating monkeys or rats or even humans in the lab. So you model the structural the temporal structure of the task, and you train the network to perform the same task and to solve the task in a supervised learning paradigm or in a reinforcement learning paradigm, which is a bit more complicated. And then what is very interesting is that you do some kind of population analysis of these, because they are white boxes, right? Because you have access to the network once it's trained, and you can study the population activity. And what it happens is that in this specific example, which I think that it's very surprising, is that once the task starts, the network is in this position, and whether one option is correct or not, the network moves, and basically the population moves towards a particular state or to another based on the environment that is outside. So there are all this range of techniques aiming, and probably more that are maybe I'm not even aware or that I missed, that try to understand not only the structure, the function, but also how these networks, how the brain actually is operating. So, but I will not talk. Of course, if there is a method to train artificial neural networks with quantum computers, it is probably interesting, and I believe that some people for sure is working on that. So that was my part of the introduction, hopefully more or less an overview of what we do, of what is done in computational and theoretical neuroscience. And all of this can obviously be applied to medicine, which is what we are actually interested in Sano, and in particular in our lab. And now I will move towards our problem in particular, the one we tried to tackle. So one of the measures that appears that is very famous also, and that is very, very used, actually one of the most used in network neuroscience and neuroimaging, is the modularity, which the original expression is this one. I will try to explain what exactly this means. But if you have a network, for example, this is the first example. I believe everyone studying network neuroscience knows about this, where you have a network and you can have two communities in this case, but the way you partition the network is not trivial, because you can partition it in many ways. So you want to have some sort of numerical ground truth or numerical criteria on how to do that. And this is what this expression here is doing. So if you have a network already partitioned in k communities, so k is an arbitrary number in this case, you can measure what is called the modularity, in the sense that this is one module, two modules, three, four, as with this sum over communities. So the first term here can be rewritten. This is very important, right? Because, yeah, this is very important. Over the links, so the edges, so the connections within the cluster. So, or I will use the word module and cluster interchangeably, or community. So it does mean the same. So basically you count how many edges are inside this community. So basically the ones that are not cut by the discontinuous line. And then you have to subtract the degrees. So the degrees is the number of connections that the node receives inside the cluster. This is a bit obscure, but it has a very nice interpretation, but I will tell more about it later, because we cannot directly use this expression to perform, to use in a quantum device. Why? Because we don't know usually. Of course, if you have a network and you ad hoc partition the network, you can use this formula. So in this case, they have this network. They have, okay, we want to have four communities. Then this is directly applicable. M is just a constant, not important in this case. But it's not the case with brain connectivity, right? Or in general, that you don't know how many communities there are in the brain. So you have to have an idea, or at least a way to try to find the best. So this is the key word, right? You want to try to find the best partition of your network. And hence the title here is just modularity maximization. So we want to partition the network in a way that maximizes this quantity here, because this is called modularity because it measures how modular is the network. So we want to have a partition that maximizes this quantity. This is our criterion to do community detection. So the first idea that pops up, and actually is a very nice one and a very simple one, is that we can define a binary variable, which is Si and Sj, which range between -1 and 1. So Si can be either 1 or -1. It's -1, for example, if it belongs to this blue community, and it's +1 if it belongs to this, to the purple community. Where's my, here, to the purple community. So if you plug this -1 and 1 to this combination here, it turns out that it's a binary. It's 0 and 1. So if the two nodes, so let's say node 1 and 2, this example, 24 and 25, belong to the same community, such is the case, this combination here is 1. If you take 24 and, for example, what number is it? 16, it's -1 + 1, and it adds up to 0. So this is a very beautiful and simplification of how can you mathematically describe if two nodes belong or not to the same community. And once you have this, let's call change of variable, or you can rewrite the modularity in a way that it's, even if for physicists, it's immediately recognizable as some sort of spin-like variable. So it's -1 and +1, and you can rewrite. We show in the paper here in the scheme, we show that we thoroughly explain how can you go from this to this. And if we want to do some modularity maximization, sorry, I forgot this. And a nicer way to implement this and to generalize this is to define the modularity matrix, which has this interpretation here. And instead of using this SI-SJ, since it is 0 and 1, you can go a bit higher, and instead of just two communities, you can do the same kind of abstraction and do an arbitrary number of communities. Simply this delta Kronecker is 1 if two nodes belong to the same community, and 0 otherwise. So this is clearly something that is familiar to physicists and hopefully also to quantum information practitioners. Here comes the link that I would like to emphasize, because this is a bit more is easier to interpret. We still have that the modularity increases within the number of edges that are inside a community. And this quantity here, it can be shown that is the number of edges that you can expect by chance to have between two nodes. So the idea of the modularity is that maximizes, so finding communities by modularity maximization is finding finding the partition that maximizes the number of edges within the community with respect to the ones you obtain by chance. And this is actually the used interpretation nowadays. So I'm assuming that more or less this part will be straight and maybe a bit clearer to everyone. but nonetheless, a brief overview to specifically emphasize the similarity between the expression in the previous slide and what is called Ising-like models. You have some sort of lattice, which is usually a square lattice, so you can also understand as a graph, but only you have connections in the first neighbors, between first neighbors, and you have the particle here or molecule has a magnetization that points up, so spin +1 and spin, and in this case -1, so it points downwards. And the energy of this system, or usually called Hamiltonian, is simply with this expression, which is this HI, which is some magnetic field that can or cannot be present in the material. And then you have the interaction between usually first neighbors, but it's not necessary, usually first neighbors, between this magnetization that points up and points down. Where the strength of the interaction between particles is measured by this coupling constant, J sub ij, that it can be either homogeneous and then it can be out of the sum or not. Interestingly, this is also generalizable to a more general type of model, which is, I believe, usually called the Potts model, where instead of having just up and down, you have 0, 1, 2, 3, 4, and there is no limit on the number of classes that you can have in a Potts model. Perhaps a more realistic interpretation of this Potts model is that this is a discretization over the angles. So a magnetic spin can be oriented not just up or down, it can have different angles, for example. And you can some sort of discretize this also. So hopefully the comparison and the similarity between an Ising-like model, so an energy-based model, and the modularity matrix is more or less intuitive at this point. And here I highlight exactly where the mapping exactly belongs, so where the mapping exactly is present, and even more here, right? Sorry. Where if you imagine an Ising model with a particular coupling constant, so measuring the interactions of -1 over m times b, you basically have an external magnetic field, and so then is not present. You essentially have the modularity expression, and this is what we will exploit, and this is what we exploit. Now we go back to the idea that we want to find the partition that best maximizes the modularity. And we have binary variables in the simplest case. So I will always do the examples in the simplest case, where you just have two communities. So your variables are either +1 or -1. So you can do brute force approach, where you simply assign randomly spin up or spin down to each one of the nodes of your network. And then you just like do either you explore the whole tree, so you keep trying and keep trying and keep trying, and then you just stay with the one that has the highest modularity based on this expression. So no optimization is done here. Or you can perform some sort of intelligent sampling of this space by, for example, doing Monte Carlo and Metropolis Hastings type of algorithm. You can do simulated annealing, or you can do also some deep learning based strategy, which are what are called energy based deep learning. So the idea is that you basically have to flip spins based on the community a particular node belongs to. And we exploit this, because I hope that it's clear that if you just try all the possible combinations that a network exhibits, this grows exponentially quickly with the number of nodes. And since I mentioned also in the beginning, we have networks in the brain that parcellate we have parcellations of the brain that are very detailed and have even 1,000 nodes. So trying this approach on those networks are impossible. And if you also want to study the air traffic networks, the global air traffic networks, of course, this is also not applicable. So you want some intelligent strategy to do this, to maximize the modularity. So we have an optimization problem, and since we have an optimization problem, we can use quantum technologies also. And in particular, quantum adiabatic optimization, which I will also go very briefly, just in case someone here is not very familiar with it. The idea of a quantum adiabatic optimization is based obviously on classical, is based on simulated annealing and classical annealing, but we use it in a quantum system. So the idea is that you basically define one Hamiltonian. So you basically prepare a system whose energy is described by two different Hamiltonians. One that is very easy to prepare and one that is accessible and that you can actually control and you for sure know its state. And another one which you don't know the ground state, which is this HP. And then you make a very slow evolution where the system slowly transitions from this very well-known stable state, and then transitions to another one, which is the one you don't know and you're not aware. And the adiabatic theorem states that if this transition is done slow enough, so basically in adiabatic conditions, the system, which will be in the ground state at the beginning, will remain in the ground state during the whole process, hence ending up at the ground state of this other Hamiltonian, which you don't know the ground state, but you know that the system will be there. And exactly if the system is at the ground state and we want to maximize some quantity, what we just have to do is to put a minus sign, and then the maximization problem becomes a minimization problem. Hence, what you want to do is you want to minimize the minimum of the modularity using quantum adiabatic optimization and quantum annealing in this case. Briefly, well, the idea is that when you use the classical thermal annealing, you just cause fluctuations. So there are thermal fluctuations, and when the landscape is changing, you expect that the fluctuations will move the particle to the other ground state. When it happens with quantum, in the quantum domain, in the quantum world, this transition is done with quantum tunneling. And we also took great care in trying to illustrate this in a clear way for non-technical readers. What you basically do is that if you have a very easy Hamiltonian in the beginning, this blue curve, and you have a very complicated Hamiltonian where the ground state, so the minimum, is not really accessible, what you do is you cause this transition. So you make these smooth transitions of this smooth evolution of the total energy of the system, and then you end up here. Basically, you remain all the time at the minimum of the Hamiltonian, and you move around it. You remain at all times at the end at the ground state of the whole system. And in this case, where the transitions are discontinuous is precisely where the quantum tunneling effect is taking place. And what we are interested in is in the minimum of this object here. And exactly this is what we do. What we do is that we essentially map our network. This is the original network defined or described by the adjacency matrix. And then you compute the modularity, and then you send this modularity matrix that takes into account the interactions between different nodes or different spins, and you send it to the quantum processor. I'm a bit short on time. And you end up with what is very well known in the quantum information realm, which is the binary quadratic model and the discrete quadratic model. What we do is basically we have used some technology in D-Wave that I will describe a bit more later, to map, to optimize this object, to map it in the quantum processor, and then the optimization is done in the quantum processor. Surprisingly, the code is extremely simple. So, of course, this is not all the code, but the mapping is done basically automatically by the D-Wave system, by the D-Wave API. You just instantiate your DQM model, your variables, and then the important part is that your DQM object takes as coupling, takes as the interaction between variables, the modularity matrix of your graph. And this is extremely simple. What we do basically is we take some networks of the brain and we use this technology and we study what kind of communities we are finding. Of course, we need to benchmark, and there are many possible options. In this case, the most used one is this what is called the Louvain community detection algorithm, which I will not explain in detail, but it basically partitions the network in a way, and then it recursively flips spins, but within these small communities, and then they iterate recursively through. And although it's a heuristic algorithm, so it is based on some heuristics, is by far the most used and probably one, if not one of the fastest ones, even for very extremely large networks. In the case of thousands of nodes, it's very large, and we take this as benchmark. Also very interesting, we don't know the ground truth of the brain, but there are some cases where a graph is created based on real data, on persons, on social interactions, and you actually know for sure where, in which community, in which social community a person belongs to. And so this is the case of the Karate Club network, which the original one is two communities, two social communities. But if you compute the spectrum of this graph, so the eigen decomposition, either 2, 3, or 4 are reasonable numbers for communities. This is called the eigengap heuristic, and it's usually taken as some sort of reliable benchmark as to how many communities you would expect to be present in a particular graph. We apply the Louvain community detection algorithm, LCDA, and the LEAP hybrid solver, which is the D-Wave solver that we are using using this mapping that I have explained now. And what we find is interesting. The number of communities is the same. The number of communities is the same, so 4. But the modularity obtained by the quantum or the hybrid quantum processor or technique is higher. So it is not the same partition that is found. Actually, if you take a closer look, what you find is that 2 communities are the same. I always forget. So the blue community here, I don't know why they are colored in a different way. Sorry, there are 2 communities that are the same. I can't find. So this one is the same as this one, and this one is the same as this one, but these 2 are different. So the sweep. So, and I believe, I can't remember now. I would have, but I don't want to waste time. There are just 1 or 2 nodes that differ. So that from this community is put here by the classical algorithm, but strangely, these very few swaps increase the modularity. And this is very interesting and puzzling, because that means that if we are trying to maximize them, finding communities that maximize the modularity, and we are finding different partitions that indeed have higher modularities, that means that the quantum processor, the quantum technique, is actually able to find finer and more difficult, but slightly better communities. And when we apply, sorry, that was stupid. My part, I had marked here that these 2 are actually the same and these 2 differ, but not a lot. Yet the modularity found is higher. There are also some drawbacks of the classical algorithm in this case, which is heuristic, so it has some sort of, it has a standard deviation of the result. it's true that it's not super high, but the standard deviation of the quantum method is well, basically low, 0. It has no variability. The drawback, as you will see also, is that the computational time is well, basically non-comparable. So this is still super fast. When we apply this to plain data, a lot of information here, but I will go. We find the same. So the modularity is always higher and significantly higher in some cases. It's higher in using the quantum annealer in both cases. So this is a functional parcellation, and this is a structural parcellation. So in the beginning, there are 2 modalities. We use these 2 modalities. And in both cases, the modularity is higher, and the stability is also higher. So we put here zeros, but it was like 10 to the minus 8. So it was like also 10 to the power of 3 or 4, even in some cases, I believe more stable, the quantum annealer than the Louvain community detection algorithm. Yet we have the drawback of the time. I will comment a bit more on this later. Interestingly, also, this is very puzzling for us also, that the number of communities is smaller. So it is not, because there is a way to hack the modularity if you just increase the number of communities. There is a point where increasing the number of communities also increases the modularity. The quantum annealer is not arbitrarily assigning new communities, but it's finding better partitions that do not necessitate smaller communities. And this is also observable in the slightly more complex and bigger network from the functional. So I will be ending now, and with some conclusions. And the key points that I would like to emphasize is that it is possible to map certain neuroscience problems to Ising-like, to energy-based optimization problems, or I call it here spin-like variables, to find, in our case, modular organizations of networks, but also to solve NP-hard problems, because modularity maximization has been proven to be an NP-hard problem, although intuitively one can think that it is indeed an NP-hard problem because it grows exponentially, the number of spin flips that you need to propose. That is potentially solving using quantum annealing, right? This is like an old idea. Quantum annealing is an old idea, but the modularity maximization using quantum annealing is not that old. Interestingly, you could optimize this function, but it is not guaranteed that that the communities you find are biologically meaningful or interpretable. And nonetheless, there is no guarantee that the algorithm will be better than the classical one, but it is, which is that it finds efficient structures, efficient community structures that are, 1, highly modular, and 2, which is very important also for us, that is biologically interpretable. So if we would go into a deeper discussion about the neuroanatomy of these clusters, it is clearly, this is the visual part, visual cortex, so it is clearly interpretable, which is also what we would like to obtain. In case of previous attempts, which is the this paper here did not use the discrete quadratic model, but used instead big binary quadratic model. So it had to do some hierarchical approach to many communities, and we do not do that. Is that we can simply obtain the partition all at once instead of going recursively into higher hierarchies. And importantly also is that you would like reproducibility in these neuro and clinical studies, because you don't want to claim something that it's not stable in terms of reproducibility. And it is also the case for the quantum annealer, that basically it's well, I would say much more stable, at least, to not be too drastic than classical heuristics, which in this case is the Louvain community detection algorithm. I would also like to emphasize that this LCDA approach is considered the state of the art. It's considered the fastest and one of the most reliable ones. So in this case, it seems to be doing a bit better. However, it has some key limitations also as well. One is the computational time that it took. The origin of this is difficult because although it is very stable, so it's not, we're not sure how the hardware plays a key in this, but the annealer, so the annealing process has to be slow enough. So that might be an important factor that is slowing things down. And also, since we are using the D-Wave computers, they are a company and they do not fully disclose what is happening inside them, but it is the way that it is also related to a third problem, which is that for now, quantum technologists cannot allocate very big networks, and recall that to solve these commutation problems, you need to have a one variable per node. So if you want to go to the 1000 limit, you would need to have 1000 variables. And pure quantum processors, as of now, cannot accommodate this size, the problems that are this big. So in this case, we are using some sort of hybrid solver that partitions the problem in a way that is not gathering all the graph at the same time and sending it to the quantum processor, but it's sending it by parts. The problem is that we don't know how this is being done because they do not disclose it. They are companies, so I believe that this is how they make their profit. And some future directions to close the loop and perhaps go to the beginning of the presentation once again, is that there are some questions that we are not addressing, and there are some questions that we would like to address. And in some cases, we are already addressing. First is that we would like to do some population studies, because in the end, what you want is this technology to be delivered and to be usable in a clinical scenario. So we have to do some population studies. We have to perhaps also do case control studies as well, and how the computational time scales. Also, when you have 200, 300, 100 participants. So it's not only about the optimization, but also the delivery time, the deployment time of these type of technologies. Also, this is perhaps more directed into the quantum community. So perhaps someone can comment on this later on, is that how far are we actually to just use pure quantum processors instead of the hybrid technologies for now. Also, since we are also want reproducibility and transparency, there are other solvers within the D-Wave platform, some that use constraints, some that are claimed to be using more pure quantum technologies. But there are other solvers I found out recently that are purely classical, but use the same kind of formulation. So once we have the formulation, if we have other solvers that use this type of formulation, this would also be very interesting for us. And then there is also this type of optimization approaches that do not use quantum annealing, but they use Hopfield networks. This actually was pointed out by one of the reviewers of our manuscript, and it is indeed very interesting, but I think that as of now, Hopfield networks have also some limitations in the implementation domain. And besides, we know the mapping from the modularity to the Hamiltonian, but we would have to map once again the modularity to the Hopfield network. And this is also some work for sure interesting to be done. And in the other case, that to really close the circle now, where we were interested in the topologies, the topology of a network is strictly related it is basically the problem of finding cliques, so small subnetworks that are fully connected. This is also an NP-hard problem, and this is also translatable. I think that no one has done that, but it's translatable to, again, spin-like formulation, so Ising-like formulation. So indeed, it is extremely interesting to find the theoretical mapping to a mathematical expression of finding cliques, so these subnetworks in a graph, in a way that it can also be used to do quantum optimization. And with that, I would like to acknowledge people involved in this, which is obviously not me, starting with Marcin and Alessandro, who are co-authors, some people in the lab that helped us, devise a non-technical description, non-quantum description of this problem, because I don't think you would want to talk about quantum physics and quantum optimization with a physician. And the next part of the process involves Katarzyna research, sorry for the pronunciation, that's a professor at AGH, and these two students, where we are aiming and we actually want to integrate this problem within a framework library, a Python library, where it's much bigger than just this particular problem, because once again, we want deployability of this technology. Obviously, thanking Sano for having me and the funding agencies as well. If anyone wants to get in touch regarding this work, here I leave some comments. And also, Alex will be presenting this work in Vienna in the International School of Network Science on July in Vienna. And here's the paper. So if anyone is interested, for sure, please go talk to him. And if it's going to Vienna. And if anyone has any questions, I will be happy to take them. Hopefully I have not overstepped my time. Thank you very much.
Hi, Joan. Can I ask?
Hello, hi Sankap. So let's maybe first thank Joan for the great presentation. So Joan, thank you. And now indeed it's time for questions. I can see some questions on our chat, but Sankap wanted to ask a question. So Sankap, please go ahead.
So basically, sorry, but Joan, it's not just a question. It's or Pavel, it's not just a question. It's just a few things I need to ask. First of all, is there any probability of working in a collaboration with Joan? And I'm pretty much interested in this field. And one more, my colleague, not colleague, one more my collaborator is also working in this quantum biology. So that was the case. So is there any probability, since they're very, is there any probability of working in a collaboration?
So as far as I don't think that would be any kind of problem. Of course, we would have to maybe take this into some private conversation. But of course, I'm open to, and I believe we are also open with Alex to at least see if there's some common ground. Of course, yes. I encourage
Definitely,
you perhaps.
I'll write you a mail.
Sorry.
Can you just pass me on your email ID so that I can write you?
Yes. Of course.
And also one more thing. Also one more thing, Joan. When you told that you cannot discuss quantum physics with a physician, well, you cannot discuss it with the Einstein either. He also never understood that. It's just a joke.
Yeah. Of course. I mean,
just to keep the things light, because
So that's why I think that it's important the way we deliver these complicated concepts.
Yeah, no, this is very interesting field. I've been trying to work in this from past 2 years. So yeah, thank you. It was a great presentation, and it was of course a great perspective of looking up things. Till now, what I was reading and working was on the molecular level of quantum physics and neurology, but the MRI part, and MRI and networking part is something great which I have not gone through. So thank you, Joan. It's quite promising.
Thank you. Yeah, for sure. You have my email, or I guess that there's a way to reach us.
Can you just supply it in the chat so that he can just copy it?
Yes, I will put my email in the chat. Yeah.
Please. Thank you very much.
Okay, great. Thank you, Sankap. Thanks, Joan, for the answer. There's also a nice comment from Marek Michalewicz. Marek, would you maybe like to unmute yourself and also give your comment, or maybe I can read it if it's fine for you. I'm not sure if Marek is with us, so maybe I'll first read the comment.
I'm reading the question, yeah.
Yes, yes. So the suggestion from Marek was to check out Atoms in Molecules by Richard Bader. It's an analog to what you were saying about modularity, but in terms of singularities of electronic densities in molecules, and that's definitely quantum. And in Marek's opinion, the key is the path, not the module. So one needs to define similarity of paths in physical sense and study tunneling of neurotransmitters between the paths that will explain so-called lateral thinking. Sounds interesting, Joan. I'm not
It
sure if
sounds
you would like to
interesting.
comment.
I took a screen capture of the question to think a bit about it after this. But so if I don't know if he's here now, but if I understand correctly, you would want to look at this not.
Yes, the
Yeah, I'm
path
not
and
sure I
not the.
understand the yeah, if he's not here, I will have to think about it a bit more.
Okay.
Yeah, sorry, but it definitely sounds interesting. Yeah.
Yes, that's fine. All right, and there was another comment or two questions from Emin Akpinar. So the first question: when you consider the noise situation in real quantum computers, what's the margin of error in the results obtained?
Yeah, that is a very good question, and we're not making strong claims on the paper because, like I said, D-Wave fully controls what you have access to. So you have access to the time, and you have access to the results. Basically, nothing else. There is. I think that Marcin looked at this with detail, but the idea is that the time is only related to the computations, so not the communication. So it does not take into account the communication from your laptop to the system. And when it comes in terms of variability of the noise and of the margin of error, you just have access. So we computed the standard deviation or the standard error that the mean is the same. And we observed that it was very small. That's the only thing that we can say, actually. What is going on in D-Wave, it's absolutely a black box, and we do not have access, and we do say that, and everyone that is using the D-Wave is also complaining about this, that you actually have no way of accessing what is happening inside. So the margin of error, I believe that as we can only report what we do, and hopefully at some point they will be more transparent. But yeah, it is a good question. It is a question. It's a concern that we also acknowledge and that we explicitly mention also in the paper.
Okay, good.
And
thanks.
there was a second one, right?
Yes, the other question is, do you have a study on MRI brain images too, such as tumor classification using quantum AI?
We don't because we were not sure, but it is one of the future. So exactly, I was giving actually ideas, and one of these is whether you have a tumor or not. Yeah, this is tricky because when you think about applicability, if someone goes to the hospital and presents symptoms of brain tumor, so standard practice is you go to do a scan or whatever scan, MRI or CT, and usually you see the tumor. So there is no real need to perform diffusion data and diffusion acquisitions if you already see that there is a tumor in some cases. But of course, there are the extension of the work is exactly to use it in clinical studies, in population studies. But perhaps brain tumor would be one that is not directly, of course, this is just my opinion, I could be absolutely wrong. You would want to find finer, more subtle diseases or impairments where the damage is actual at the network level rather than at the let's call, anatomical level. But of course, it's a possibility. We have not done that. We have think about it, and it's very cool research as well. I mean, if after this quantum process, you can automatically also differentiate between two different classes, that means that, again, it is finding some meaning. Quantum processor, it is actually meaningful, and it's not finding rubbish and organizing it in a very intelligent way. So it is a very good idea.
Okay, good. Thanks. There's another question from Mateusz. How big of an aggregate of actual neurons acts as a single node in the problem of neuroscience? Or you take an approach of taking parts of brain that previously are known to function as they are and label them as nodes instead?
Yeah, this is a very good question also. The answer is depends, like usually, right? It depends on the amount of detail you want to describe and you want to capture. So there are many different parcellations available, freely available. Each one is useful for some problems. Each one is useful for some others. It's important to distinguish that anatomical parcellation, so structural parcellation, is not directly usable to study functionals or to study activity. And even you can go to the extreme case of not using brain parcellation and treating the voxel, so the pixel, but in 3D, of your images as one node itself. So typically they are between 1 millimeter cube millimeter and 2-3 millimeter cube, and within this, how many neurons can they be inside? I don't want to say something that is wrong, but for sure not just one neuron. So of course you lose some resolution.
Yep, thanks. Someone wanted to ask a follow-up question.
Sorry, there was a second one. I will try to briefly answer that.
Yes.
Were you taking everything in Yeah. This is usually how you do it in functional. You compute your correlations, the whole brain, and then you try to do some independent component analysis or some clustering on that. And if something works, particularly if something is super similar, you take this as one entity. But there are many methods to do that also. Depends on what you want to study. Yeah.
All right, great. Do we have more questions from our participants? I don't see more questions on our chat. So actually I have one more question. You compared this hybrid quantum annealing approach with the classical algorithm, and you mentioned that this algorithm was considered as state-of-the-art for this NP-hard problem. So I was wondering if you maybe have already compared this approach with some other algorithms, because in case of NP-hard problems, the performance of particular algorithms, particular heuristics, may also strongly depend on the instances. So I was just wondering, because this classical algorithm that you investigated, as you said, was considered a state-of-the-art. So here, in terms of the efficiency or the quality of the solution that was found by this hybrid method, maybe we can say that we have some advantage over this classical algorithm. But maybe there are some other classical algorithms that could give equally good or maybe even better results for these instances.
Yes. The short answer is yes, I agree with you. However, I think that there are probably close to more algorithms trying that solve this problem than inhabitants in Krakow, maybe. There are a lot of them, yeah. But there was when this modularity was proposed in 2002, 2003, you can actually find an explosion of papers trying to tackle this problem that they somehow condensed and finished in this Louvain in 2008, 2009, because it was believed that that's the best you can go for big networks. It is true that there is an improvement, a small improvement. It's called what's the Leiden, but the it's not significant in terms of sorry, it is significant, but it is not a big improvement.
Mm-hmm.
Of the we are only talking about small ones, like the same order, yes. Perhaps even less than the ones we found here. Mm-hmm. So it is true that the instances will and the node ordering. So the adjacency matrix is not, so the graph is invariant to permutations, but the matrix itself is not. So that can also impact the performance. But I would like to comment something because we thought about this. But what this Louvain algorithm is doing, essentially, if not explicitly, is just sampling the spin space. I don't know, the state space, mm-hmm. right? But it does it in a very particular way, which is fast. But eventually, what the quantum part, the quantum process is doing, is the same, but it's not strictly restricted by the energy barriers. Mm-hmm. So, in theory, what I came to understand is that if you use a quantum approach, you're not restricted by how complicated or fine-grained is the space, is the energy landscape, because mm-hmm. you can tunnel through it, right? Mm-hmm. So it doesn't matter how complicated, and it actually can go there, and that is how we try to explain that it is finding higher modularities, but with different partition.
Okay.
That is not found by the classical.
Mm-hmm.
But of course, it's true that you probably, to do a complete survey, that would probably be a review paper on itself. Yeah.
All right, good. Thanks for the answer. I don't see more questions now on our chat, so I think we can conclude. So Joan, first of all, thank you once again for the great presentation and answering all the questions. I believe it was very fruitful discussion, so we learned a lot.
Thank you.
Yes, so maybe I will, before I stop recording, I will now just share some last slides.
I will stop sharing then, yeah.
Yes, just to announce the next meetup, because we already have some plans. So yeah, all right. Okay, so yeah, that was the meetup that we had today, and the next episode of Warsaw Quantum Computing Group will be in June. It will be online only as well. And the speaker will be Marco Fellows Asiani, so he's from University of Warsaw. The title is still to be determined, so we'll announce it probably at the beginning of June or end of May. And yeah, we would like to thank once again our strategic partners, Kogit, Narto, and Sonovero R&D for supporting us, as well as our honorary partners, including Sano, of course. And if you like our meetups, if you like our events, let's stay in touch. You can join our groups or will be the recording from this lecture. Yes, someone wanted to say something, I guess.
Pavel, actually, sorry, this is Sankalp once again. Okay. And honestly, I really like, I just recently came to know that you have a series of lectures going on, on such a great topics. Okay. So
all right.
I would request you, and you can kindly, just add me into your group and, constantly keep on, adding me in the meeting, because I'm pretty much interested in this quantum biology. So, and apart from that, many interesting things. Okay, so it's just a humble request to you, please.
Okay, so of course you can join our mailing list, and all our groups are open. So of course, the approval is necessary. But once you join or apply, we'll add you to these groups. And in particular, when you signed up for the meetup using Google Forms, there was an option to be just directly added to our mailing list. So if you
I will definitely do that. Okay, I'll definitely look up, and I'll definitely first of all send you a connection request on LinkedIn, and
okay.
later on further. Okay, thank you,
Okay,
Paul,
that's good.
for creating
Thank
such a
you.
good lecture.
Yes. So there's another question whether there will be any meeting in person in the near future. I'm not sure. So we have some plans to, or some ideas to organize an on-site meeting in July, but it's not confirmed yet. So it depends on many things. But keep your fingers crossed, because as some of you remember, because we had some participants of our previous meetups, we had an on-site meetup in March this year. So it was 2 months ago, and it was quite successful. We invited a speaker from Oxford University. And we have some ideas for the next on-site stationary meetup in Warsaw in July, but it's still, let's say, under construction. So we have to just organize some things first, and there will be announcements, of course. So stay tuned. Please follow our profiles, our groups, and for sure you'll be notified our future events. So with this, I would like to thank all of you for participating and for your attention, for very interesting discussion and good questions. Joan and Alex, I believe that Alex is still maybe with us. So thanks for this very interesting material, and congratulations on your results. It's really significant, as you said, and that's good that you are working on these topics. And we hope to see all of you next time. During our next meetups, or maybe in Sano in Krakow, we'll see. So with this,
for sure, that would be very nice. Yeah.
Great. With this, I will conclude, and I will just stop recording. Okay. And yeah, as I said, we'll do our best to just publish the recording later on our YouTube channel. So thank you once again. Thanks everyone. Have a good evening, and bye bye. Good luck.
Thank you, Pavel. Thank you.
Thanks.